Warm welcome. Good afternoon. Uh, we have today a very able speaker, Mr. Shantanu Sen. Already the participants have seen his vast knowledge on the refinery operations. He delivered in the last day a lecture that is on Haldia refinery overview. So today, Mr. Sen, the Chief Technical Services Manager, Indian Oil Corporation Limited, Haldia refinery, he will deliver his lecture. Sir will present the topic that is the refinery operations. I request all the participants to listen to, take the notes, handouts, because you see, when you will be preparing the report, then it will be very much necessary to all these points. So please jot down those points. I also invite our respected coordinator, Mr. Ashanendu Mondal. So he is also is present here. So I request Mr. Sen to start his deliberation. Mr. Sen, please unmute yourself, sir.
Thank you, Mohit. So I will off my video for the presentation.
Oh, surely.
Maharaj, am I audible?
Yes, sir. Yes, sir.
And the screen is visible?
Yes.
Yes.
Very clear.
So I'm starting.
Yes.
So today's topic is an approach to refining processes. In a refinery, various types of processes are involved for refining a crude oil to reach at marketable product. So there are several factors which guide the refining process. One is environmental norms, one is customer preferences, and the other is customers' capability to convert that product into several other downstream products. So apart from MS, that is petrol, and HSD, which is consumed by the customers, there are several other products which are also marketed by a oil refining company like naphtha. So what the customer will do with that naphtha, that also affects the refining process, or that also affects that also guides to choose the configuration of the refinery. And customer preference, always there are customer preferences for various products, for upgraded products. So for that we need secondary processing units to build our capability. So in a nutshell, a refinery uses crude oil as feed and delivers product to the market. So in between these two steps, there are primary processing units, secondary processing units, and dispatch facilities, of course. So I will come one by one. So how from crude oil we reach the marketable product, or what is the procedure we apply in a particular refinery. Maybe one process is there, in another refinery maybe another process is there. So it depends upon the configuration which is being chosen. at the time of building that refinery. So while putting a greenfield refinery, that means a grassroots refinery, normally on date, like Paradip refinery, which is the latest refinery, the processes are selected based on latest technologies. But in refineries which are old, maybe 20, 25, 30 years old, so they are to meet the customer preferences or customers needs, to meet the customer needs, we have to modify our present operating units, or we have to put another unit as an auxiliary to the existing unit. So these are brownfield refinement modifications. That means modifications on the existing setup. Greenfield one is grassroots one. That means building a refinery from zero. That means on a laden land, a refinery is being built or a particular unit is being built. That is called greenfield refinery or grassroots refinery. But while we modify one existing facility based upon the customer's preferences or based upon the profitability or for sustenance, then it is called brownfield brownfield project or brownfield modifications. So this is the difference between greenfield and brownfield. Beginning of the petroleum refining in India, while talking about these, we have to cite Digboy refinery, which is the oldest refinery in India. Particularly, this refinery belongs to Indian Oil, and we take pride that we have the oldest refinery. Digboy refinery in 1890s, it was built. It was commissioned in 1901, and in 1890s, what equipments we are using for distilling a crude? That is a steel, basically. That steel is there. The fast steel. This is kept in front of the refinery on date also. Anybody can see or anybody can visit this. So this is a preliminary equipment used for refining a crude oil in the 1890s. But if we see today, we have changed the refinery processes a lot, and we are not using steels, we are using columns, we are using secondary processing facilities like INMAX, FCC, hydrocracker. So coming to the processes in a refinery, we find that there are physical processes, there are thermal processes, there are catalytic processes, there are conversion of heavy residues. This particular step number 5 is important because selling a heavy residue may not be profitable at times, and we may need to convert those heavy residues into distillates for improvement of distillate yield and profitability. And the 6th one is treatment of refinery gas streams. So basic refinery operations comprise of the major 3 processes. One is separation processes, which is primary processes, or you can say this is atmospheric and vacuum distillation processes. Second one is conversion processes, which are secondary processes. This conversion process may not give the finished product, but produce intermediate stocks, which can be further treated into finishing processes to get the marketable product. Basically, the third part, the finishing processes, these include removal of contaminants like sulfur, nitrogen, etc. for meeting the stringent environmental norms. So earlier in 1890s, only the separation processes were used, like the steel you have seen, which is being kept in front of the Big Boy refinery. Later on, conversion processes are added, and to meet the environmental requirement, several finishing processes have been added subsequently. So this is the process how hydrocarbon molecules in crude which do not meet the customer's requirement can be converted into marketable products. So coming to the primary processes, we see there is the first step is desalting. After receiving crude in the tank, we normally give a settling time of 24 hours to settle down the water part. Then we drain the water, or if we at all do not drain the water, we send the crude to desalter. After desalting, the water from the crude is separated, and the crude portion, which contains minimum amount of oil, is being fed to the distillation columns. Crude oil often contains water, inorganic salts, suspended solids, and water soluble trace metals. This water, if we put into primary processes without segregating, then it will lead to different kind of problems in the primary processes. In the secondary processes, it will lead to corrosion, plugging, fouling of equipments, etc. So the method of crude desalting is important before putting the dewatered crude into the topping column or into the pre-fractionator. I will come on pre-fractionator part later on. So what happens in desalting is basically adding some surfactant materials or demulsifiers into the system, into the vessel, which is called desalter, and putting some electric current into that system. So by this way, water will get separated, and from the boot of the desalter, we drain out the water. That water goes to effluent treatment plant. And the dewatered crude, which is free from water and some of the contaminants along with water, those are separated. So this crude, dewatered crude, is getting fed into PF column or pre-fractionator column. Before putting that crude into the pre-fractionator column, we have furnaces to ramp up the temperature. The refining process, as you can see in the step 1, it is a separation of crude oil into various fractions or straight run cuts. This straight run cuts, what is important? The word cut is also important. Straight run means which is directly coming out from the CDU or VDU. Cut means it is specified by a particular initial boiling point and final boiling point. So cuts are temperature ranges between which that particular cut is separated. Now coming to the, I will skip some of the slides because those are not important, because description that I will describe. The crude oil in this simplified block flow diagram, you can see the crude oil, what comes out from the tank, or from the tank it is being pumped to the desalter at a temperature range of 130 to 140 degrees Celsius with the aid of desalting demulsifiers and with the aid of high voltage electrostatic current, the water is getting separated. The dewatered crude then is fed into the pre-topping column. Pre-topping column is nothing but it is an annexure to the atmospheric or crude distillation column. Because some of the crudes contain lighter fractions and those may overload the lighter section of the crude distillation unit. So in the pre-topping column or in the pre-fractionator, what we do, at a particular temperature of 200 degrees Celsius, we distill out, and there are two products which is coming out from the pre-topping column. One is unstabilized naphtha and the other is the balance part. So unstabilized naphtha, we are separating prior to feed the crude into the CDU or crude distillation unit to reduce the load of the crude distillation unit. The unstabilized naphtha, which is coming out from the top of the pre-topping column, is then fed into stabilizer, from where LPG is recovered and stabilized naphtha is getting generated. The LPG which is getting generated from the stabilizer top is put into LPG treatment units, and the bottom product of the stabilizer, it is taken into naphtha tank. So majority of the naphtha and LPG part, which are the lighter ends of the crude, are getting separated into pre-topping column. Still some amount of naphtha and some amount of LPG will remain into the pre-fractionator bottom, which is further treated into a furnace to ramp up the temperature up to 370 degrees Celsius, and then it is fed into the crude distillation column. From crude distillation column, again some amount of naphtha will get generated, which is light naphtha. At the top you can see light naphtha. It is taken into tank. Heavy naphtha, it is sent for further desulfurization process. The kero cut, it is taken into tank, from where it is fed to the kero hydro desulfurization processes for production of kerosene or ATF. The light atmospheric gas oil part, the LGO or LAGO, is taken into the tank. Again, there is a series of desulfurization processes like diesel hydro desulfurization processes is there, or diesel hydro treatment processes is there. So we take into those units to produce finished diesel. The heavy atmospheric gas oil part, it is also diesel component, but it might not meet the specification of the diesel in terms of recovery at 360 degrees Celsius. So we separately put it as a separate product, which is named as JBO or jute batching oil, or we can put this HGO to hydrocracker unit or DHDT unit. Now, each and every time I am talking about tanks. Kero, it is taken into tank, then taken into kero hydro desulfurization process. LGO it is taken into tank, then it is fed. In modern refineries, the concept of tank is not there. The hot kero stream from the atmospheric distillation column is directly fed into the kero hydrodesulfurization process, or in case of LGO, it is directly fed to the DSDS or DSDT unit. So, basically, what is the necessity of the tanks in between? Tanks in between, which are in between the crude distillation unit and the secondary processes, those actually act like a surge. So in case the CDU is down, then with the stored material, the downstream processes can operate for some period, say 4 hours, 5 hours, 10 hours, depending upon the capacity. Similarly, the downstream units are down, then the crude unit can run for a certain period by storing those material into the tanks. But in modern refineries, there is no tank concept, because if we put these materials into tank and from there we process into secondary treatment processes, then there is a temperature drop. Then again we have to increase the temperature by addition of additional heat for which fuel will be consumed. So it will incur additional fuel and loss. Where the hot feed is fed to the secondary processes, the fuel and loss will be comparatively lower, because there is no such tank mechanism of storing the material into tank and then feeding it to secondary processing units. So there are advantages and disadvantages of both the processes. In case of hot feed, which is used in modern refineries, if the crude distillation is down, then the secondary units are also down. But if there are intermediate tanks, then we can sustain for some period. So there are pros and cons of both the processes. So the reduced, now coming to the reduced crude oil, the RCO, which is not getting distilled out into the crude distillation unit at atmospheric pressure, is being fed to the furnace to ramp up the temperature up to 415 to 430 degrees Celsius. And the hot feed is fed to the vacuum column. Vacuum is typically 40 to 60 millimeter Hg absolute. So in vacuum distillation column, the distillates which were entrapped into the RCO and was not getting separated at atmospheric pressure will come out as light vacuum gas oil, heavy vacuum gas oil, and the part which is not getting distilled at this vacuum and at this temperature will come out as vacuum residue. So basically here straight run products are light naphtha, heavy naphtha, kero, LGO, AGO, LVGO, HVGO. These are straight run products. LPG, these are straight run products. These are called SR LPG, SR naphtha, SR kero, SR LGO, SR HGO, like this. Straight run LGO, straight run HGO, straight run LVGO, straight run HVGO, like this. So this is the basic block flow diagram of a crude distillation unit. Now, to take advantage of the heat of the products which are coming out from these units, there are a series of exchangers. These exchangers take heat from the products and give heat to the crude oil. So kero versus crude exchanger, HGO versus crude exchanger, HGO versus crude exchanger. So with these, the temperature of the streams which are going to the tank is coming down, and subsequently that particular heat is being utilized in heating the crude before feeding it to desalter. So there are several interconnected exchangers in between, which are basically finished product to the crude oil exchangers mainly. Now coming to the cut range of these products, naphtha is basically 30 to 140. I will not say 30, I will say C5 to 140, because why I am saying C5 to 140? C5 is carbon number 5. That means molecules which contain 5 carbon atoms. Because up to LPG, C3 and C4 get separated. So what comes into naphtha is C5 plus and up to 140 degrees Celsius. Up to 140 to 270 it is kerosene, and 140 to 240 it is ATF. Similarly, 240 to 360 or 370 is gas oil, and above 370 is reduced crude oil. Now, what are the applications of these streams? The gas which is coming out from the crude distillation unit, that is used as refinery fuel. That is basically fuel gas. That is used for firing into the furnaces. LPG, what is coming out from the CDU unit, is further treated into LPG Merox, and we get domestic or industrial LPG. Naphtha, which is coming out, that is C5-140. It is it is having two dispositions. The first one is MS blend, and the second one is petrochemicals. The third one is fertilizer, of course. So MS blend, in MS blend, we normally prefer 110 to 140 cut, and we get strip of the C5 to 110 part, and the C5 110 part normally goes to petrochemical or fertilizer, and 110 140 cut goes to MS blend. The kerosene part, it is used as domestic fuel or as jet fuel. The gas oil which is coming out is a feed to the diesel dehydrodesulfurization. And the reduced crude oil, it is fed to the vacuum distillation. So none of these products are finished products which are coming out from the CDU. Those are further treated to get the desired product. And other than LPG and naphtha, nothing is the final product which is going to the product pool. Kerosene is further treated, gas oil is further treated, and RCO is further distilled. So basically SR LPG and SR naphtha, these are the two finished products which are coming out from the CDU process. Coming to this naphtha part, naphtha, which is C5-140, it normally is being fed to the naphtha splitter. Naphtha splitter splits this naphtha into three parts. One is C5 70 degrees Celsius, one is 70 to 90 degrees Celsius, the other is 90 to 110 degrees Celsius, and the last one is 110 to 140 degrees Celsius. This is done into naphtha splitter column. So this split, this naphtha which is splitted into naphtha splitter column is being disposed in different is getting disposed. The C5 90 part, it goes to the tank. 90 to 110 part, it goes to catalytic reforming unit. And 110 140 cut also goes to catalytic reforming. The 70-90 cut goes to the isomerization. Isomerization unit, what it does? Isomerization unit, it isomerizes the straight run components, and through isomerization, the octane number increases. What is important for this naphtha to be consumed into the MS blend is octane number. Naphtha is predominantly having lower octane number to the tune of 60 or 70, in between 60 and 70. but for MS we require 91 plus. So we have various processing units for converting this low octane naphtha into high octane naphtha. One is catalytic reforming unit, the other is isomerization unit, the other one is alkylation unit. So what catalytic reforming unit is doing, it is basically taking the 110 140 cut or sometimes 90 140 cut and is reforming the molecules. So by reforming the molecules of this straight run naphtha, we get octane to the tune of 99 through catalytic reforming, and the product is called reformate. So the feed is naphtha. Feed is a particular cut of naphtha. The process is catalytic reforming, and the product is reformate, which is having high octane number compared to the feed naphtha. Similarly, what isomerization does, it takes the C570 or C590 cut and isomerizes those straight run components and increase the octane number, not to that extent of catalytic reforming unit, but to some extent to the tune of 80 or 82 or 85. So isomerization process, the feed is naphtha, the product is isomerate, the process is isomerization, and the outcome is octane number enhancement. The feed is having 60 to 70 octane number, and isomerate is having 85 octane number. So basically, these are components of the MS blend. So MS is a blended product. So two components we are finding over here. One is reformate, another one is isomerate. Another process which is not written over here is alkylation process. Alkylation process normally uses C4 component, that is part of LPG, C4 component. LPG is C3 plus C4. The C4 component of the LPG is being used in alkylation process. So the feed is C4 strings, the process is alkylation, and the product is alkylate. Alkylate will have an octane number to the tune of 120. So this is another MS blend component. The other MS blend components will come in subsequent slides. So basically we got three components of the MS blend, one reformate, one isomerate, one alkylate. So three streams we get over here. Balance जो kerosene and gas oil, these are single streams going to the unit, and after hydro treatment or after Marox treatment, it is going as kerosene or ATF. Gas oil, it contains sulfur to the tune of 1.5 to 2%. It is going to the diesel hydro treatment processes, and the sulfur content is reduced to the desired extent. Now coming to the catalytic reforming reactions. Basically what we can see, lean naphtha, it is having high paraffin, which is basically C590 part. The heavy naphtha part, which is 90 to 110, that is getting reformed into the catalytic reforming unit, and the aromatics part increases substantially. This aromatics lead to high octane number, and paraffins reduces because those paraffins are converted into aromatic. Basically, aromatics we are getting at the cost of naphthalene and paraffins. So basically what happens, in naphtha paraffin was more, which is the lean naphtha. So this high paraffin lean naphtha or light naphtha or C590, whatever you can say, this is a very good feed for petrochemical, like Haldia Petrochemical, who are taking this naphtha and cracking it to produce ethylene and propylene. So more the paraffin in naphtha, the more the yield of ethylene and propylene. So lean naphtha or light naphtha is a very good fit for petrochemicals. And in reformate, we can see the paraffin is very less and the majority part is aromatics. Now, as I have told, it is a MS, it is a MS component. Now, MS has a specification of aromatics, which is 35% volume. So, if we use this reformate entirely into MS as a single component, then it will fail into aromatics, because aromatics will be to the tune of 80% in reformate, but the finished MS blend is 35%. So we have to reduce the aromatics. So what we can blend with that? One is isomerate. Isomerate contains no aromatics. We can blend to alkylate. Alkylate contains no aromatics. So if we mix these three strains, alkylate, isomerate, and reformate, then we can bring down the aromatics to the tune of 35%, which is the specification of the MS. So, and side by side, the octane number of the reformate comes down by using isomerate, because isomerate is having octane number of 85. So by using reformate and isomerate, we can reduce the octane number of reformate from 99 to 91 and substantially upgrade isomerate, whose octane number is 85, from 85 to 91. Side by side, the aromatics of the reformate, which is to the tune of 80% volume, that comes down because isomerate is having no benzene or no aromatics. So the benzene or aromatics specification is also met. That's why MS is a blended component, and MS is not a single stream. In any of the refineries you can find, MS is always a blended component, because specification has been set in such a way to minimize the environmental impact, to maximize the performance of the engine. So by setting the octane number of MS at 91, the engine performance is getting improved, the anti-knock property of the fuel is getting improved, and side by reducing the aromatics content into the finished MS blend to the tune of 35% and benzene content to the tune of 1% volume, the environmental impact is also mitigated. Now coming to the next slide. This is one semi-regenerative catalytic reforming unit. Naphtha, the pre-treated naphtha, pre-treated, why we are saying pre-treated? Before sending the naphtha into the catalytic reforming unit, we have to reduce the sulfur content, because the catalyst which is being used in catalytic reforming unit is prone to deactivation at the presence of sulfur. So sulfur is a contaminant for the catalyst which is being used in the catalytic reforming unit. So we have to treat the naphtha or hydrotreat the naphtha to get rid of sulfur and nitrogen. After the pre-treatment of the naphtha, it is fed to a series of reactors. And in the reforming process, we get reformate as a product and hydrogen as a byproduct. LPG is also as a byproduct. Part of the hydrogen is getting recycled, and the balanced hydrogen is being sent to the hydrogen pool, from where various hydrotreatment facilities take their hydrogen. The C4 stream, which is coming out from the catalytic reforming process, it is sent to the LPG pool. And the reformate which is the main product, which is around 82 to 84% of yield, that is stored into a separate tank for further use in MS blend. So how the different process variables impact the product quality, the pressure of the catalytic reforming process, RON will go down, reformate yield will go down, and coke deposit in the catalyst will be less. Similarly, if we increase the temperature, the RON of the reformate will go up, the yield of reformate will go down, and the coke deposit on the catalyst will increase. So temperature and pressure plays a very important role because we have to optimize between the RON and the reformate yield. If the yield is more, the RON is less, or if the RON is more, yield is less, we have to optimize between these two, and we have to set the temperature and pressure in such a way so that it meets the design yield of 82 to 84%, and side by side the octane number remains to the tune of 99 to 102. Nowadays, in greenfield refineries, this semi-regenerative kind of reformers are not used, because semi-regenerative kind of reformers, those have to be regenerated by taking shutdown after 1.5 years or 2 years for regeneration of the catalyst. But in continuous catalytic reforming unit, there is a regenerator, which removes the coke from the catalyst, and the catalyst is continuously recycled in reactors. So this kind of catalytic reforming units does not require shutdowns in every 1.5 year or 2 year, and they can run continuously. So preferably continuous catalytic reforming unit is profitable, but in old refineries, still there are semi-regenerative kind of catalytic reforming units. Now coming to the diesel desulfurization. Diesel desulfurization can use LGO or LAGO and the vacuum gas oil as feed. There are various other feeds from the secondary processes also that I will come later on, like FCC LCO, or you can say the FCC heavy cycle naphtha. Those can also be fed into DSDS. So it's a high pressure process. DSDT is more high pressure process than the DSDS. DSDS operates at 35 to 40 kg per centimeter square. So after the reaction, the sulfur part gets converted into H2S and goes to the absorber, and from there it is sent to the sulfur recovery unit. The diesel part, which is desulfurized, is getting stripped off, and while naphtha is getting separated from that, and desulfurized diesel comes out from the bottom of the stripper. The need of separating the wild naphtha from this stripper is basically on account of low cetane number, because diesel has a specification of 51 cetane number, but the naphtha will have less cetane number to the tune of 35 to 40. So basically, if we do not recover this naphtha heat from here, that naphtha will be entrapped into the diesel part and will make the cetane number of diesel lower. So again, we have to add external chemicals like cetane improver, which are costlier, to make the cetane number to the tune of 51. So naphtha will be blended into diesel desulfurization process. Naphtha will be separated. Sometimes, but not in DSDS, but in DSDT, the desulfurized diesel will have certain number to the tune of 56, 58, at times 60 also. And the density remains, or specific gravity remains as 0.85. Flash point also remains high as 55. So in case of DSDT, we can put this wild naphtha into desulfurized diesel, because desulfurized diesel is having high Cetane number, high flash point, and high density. So this wild naphtha can be absorbed in the desulfurized diesel of the DSDT process, but not in DSDS process. So basically, what is the difference between the DSDS and DSDT process? DSDS operates at a temperature of 40 to 50, while DSDT will be at a pressure of 90 to 110. And the temperature which is used in DSDS is 340 to 390, and in DSDT it is 330 to 370 degrees Celsius. If we see the product pattern, we can see in DSDS process off gas is 1.4%, wild naphtha is 1.3%, and diesel is 97%. In DSDT process, the off gas is 1.8, wild naphtha is 2.0, and diesel is 96.1. Now, based on the situation and based on the quality of the finished diesel of the DSDT process, where the Cetane numbers remains to the tune of 60, flash point remains to the tune of 60 degrees Celsius, and density 0.85 plus, there we can drop the wild naphtha. This 2% wild naphtha can be dropped, and the entire diesel yield will be 98.1. So DSDT process is favorable compared to DSDS process, and all the greenfield refineries today are going for DSDT, not for DSDS. DSDS is only available there where the refinery was built in 30-40 years ago or so. Now, coming to the vacuum distillation products, one is VGO, vacuum gas oil. This SO, LO, IO, these are also part of vacuum gas oil. We normally do not separate those until and otherwise it is required for further secondary processes or lube oil products. This SO, LO, IO are separated from the vacuum gas oil in lube refineries. But in non-lube refineries, there is no need of segregation of this SO, LO, IO. VGO will come out as one stream, HVGO will come out as a separate stream, and vacuum slop, some amount of vacuum slop is required, recovered, and vacuum residue. So in non-lube refineries and in modern lube refineries, there are 4 cards: vacuum gas oil, HVGO, vacuum slop, and vacuum residue. But in refineries which are producing lubes in conventional processes, there will be 5-6 cards like vacuum gas oil, spindle oil, light oil, inter oil, heavy vacuum gas oil, vacuum slop, and vacuum residue. So this is depending upon the finished product which we are going to produce. Coming to the lube-based oil processing. Earlier, lube-based oil processing was guided by crude selection or multi-step manufacturing processes. But in modern refineries, this lube production depends to some extent on crude selection, but there is no multi-step manufacturing processes. In modern refineries, there are catalytic processes for dewaxing, But in older refineries, there is conventional processes of solvent dewaxing, solvent extraction, and hydrofinishing. So basically, I will not go deep inside the base oil. If I have time, I will tell about the base oil and base oil properties. I will go to the secondary treatment units. I am skipping all these things because these are not prerequisites of today's discussion. Now coming to the fluidized catalytic cracking unit. What I have told, VGO, which is coming out from the vacuum distillation unit, requires further treatment. And in the earlier session, day before yesterday, I told there are two dispositions for this vacuum gas oil. One is fluidized catalytic cracking unit, the other is hydrocracker. What fluidized catalytic cracking unit does is it converts the vacuum gas oil to valuable distillates like LPG, gasoline, diesel, etc. by catalytic cracking process in fluidized bed. Feed, it varies from the refinery to refinery because some refineries are having FCC, some refineries are having RFCC, which is resid FCC, some refineries are having VGO FCC, and rest of the refineries are having Petro FCC or INMAX. So in FCC, VGO is the feed. In RFCC, VGO along with RCO and VR is the feed. And in INMAX, hydrotreated VGO is the feed. Nowadays, after the incorporation of the hydrocracker unit, the unconverted part of the hydrocracker, which is hydrocracker bottom, that is also fed to FCC. So this is a FCC unit where feed is treated into the reactor in which the catalyst is in fluidized pattern, and after the reaction, the catalyst part goes to the regenerator and it comes back again into the reactor from the regenerator. So it is a continuous process. After the reaction, whatever streams are getting produced, those are splitted into several products like LPG, naphtha, light cycle oil, heavy cycle oil, and sludge oil. LPG goes to the LPG pool, light naphtha goes to MS. Light cycle oil goes to DSDS or DSDT, and heavy cycle oil it goes to coker, slurry oil it goes to coker. Or the refineries which are not having cokers, those are using the slurry oil or heavy cycle oil into FO blend, furnace oil blend. So I will come to the comparison between different types of FCC. One is VGO FCC, it treats VGO as feed. One is resid FCC, it takes VGO, VR, and RCO as feed. One is INMAX, which takes VGO as a feed or VGO plus VR as a feed, depending upon the configuration. And one is Petro FCC, which is the modern version of the INMAX. If we see the yield pattern, the LPG yield and propylene yield, these are the guiding factors for selection of FCC for a particular refinery. Say the refinery which is producing LPG as a product will choose VGO FCC or RFCC as their choice. But those refineries which are integrated with petrochemical plants, those will obviously choose INMAX or Petro FCC, because if you see, there is a paradigm shift of yield of LPG and propylene in INMAX and Petro FCC as compared to VGO FCC or RFCC. It is almost double. In INMAX, we get 16% LPG and 11% propylene, whereas in Petro FCC we get 20% LPG and 22% propylene. So everything is at the cost of diesel. So LPG prices or propylene prices being more than diesel, Petro FCC is nowadays a viable option for any greenfield refinery, because nowadays all greenfield refineries are integrated with petrochemical plants. So they can send this propylene directly to propylene recovery unit, or they can send the LPG or propylene mixture to propylene recovery unit. From there, they will segregate the propylene part, send that propylene part to the polypropylene unit for production of polypropylene. The price of polypropylene is almost double of the price of diesel. So nowadays, INMAX or Petro FCC are the viable options compared to conventional refineries which are having VGO FCC or resid FCC. The other unit which can consume VGO as a feed is hydrocracker unit. The objective of this unit is to convert the vacuum gas oil into valuable distillates like LPG, naphtha, kerosene or ATF, and diesel. And the unconverted part will go back to the FCC in once through hydrocracker unit. But in hydrocracker unit, which are not once through, the UCO or unconverted part will again be fed into the chain of reactors for converting the unconverted oil into further LPG, naphtha, ATF, and diesel. So basically, the hydrocracking unit or once through hydrocracking unit, these are based on the choice of the refiner. Those who are producing lubes like Haldia refinery will go for once through hydrocracking unit, because the unconverted oil is a very good feed for FCC as well as lubes. But the refineries which are not having lube producing facilities, those will go directly to hydrocracking. So hydrocracking is a multi-stage once through hydrocracker kind of thing, where the unconverted oil is further treated to produce valuable product. Like Haldia refinery, where lube oil is getting produced, we are having once through hydrocracker unit. But in refineries like Panipat, there is no once through hydrocracking unit. There is hydrocracking unit, because unconverted oil will not go to the lube part, or they can use once through hydrocracker unit if they want to send the unconverted oil to FCC, where FCC is having spare capacity. So basically, hydrocracker unit operates at a higher temperature of 370 to 420, at a system pressure of 160 to 170, and the catalysts are mainly NEMO based. So this is one schematic flow diagram of one hydrocracker unit. This is not once through hydrocracker unit. In once through hydrocracker unit, the conversion remains to the tune of 75%, and basically 25% is unconverted. But in hydrocracker unit, which is multi-stage hydrocracker unit, there the unconverted oil generation will be to the tune of 5%. So more conversion is available from the hydrocracker rather than once through hydrocracker. Now, the last one being delayed coking process. Refineries which are older, those are not having the bottom of the barrel upgradation facility. That means the black oil which is coming out from the bottom of vacuum vacuum distillation unit, which is a VR or SR, short residue or vacuum residue. That vacuum residue normally used in conventional refineries in production of furnace oil or in production of bitumen. The modern refineries are having delayed coking process, which takes the vacuum residue as feed and converts it into LPG, light vacuum gas oil, heavy vacuum gas oil, and petroleum coke. So basically, in delayed coking process, we get more distillates rather than conventional refineries where VR is used in FO or bitumen pool. None of the products which is coming out from the delayed coking process is finished product, and each and every product in the intermediate products which are getting generated in DCU are further treated to get the desired product. So this is the schematic of a simple delayed coker unit where feed is the vacuum residue and the products are gas oil, naphtha, kero, and fuel oil. This fuel oil is also heavy coker gas oil, we can further treat it, and petroleum coke. Delayed coker unit does not produce any finished product, and all the intermediate products like LPG, which is having high markup tanks, high unsaturates, is further treated into Merox or caustic wash. Naphtha, which is low octane, high olefin, is further treated into naphtha hydrotreater or DSDT. Kerosene, which is having high saturates, kerosene or light coker gas oil, it is sent to DSDT. Gas oil, which is heavy coker gas oil, which is having low cetane number, is sent to mild hydrocracker or FCC. And the petroleum coke, as it is being sold as pet coke. In modern refineries, they have facilities to further upgrade the coke also. That is called coke gasification process. So by gasification of coke, we can get further distillates. So some of the refineries in India are having the coke gasification units, whereas most of the refineries are not having. And those who are not having the coke gasification unit are facing problems in disposal of coke, because based on environmental norms, firing of coke has to be in such a way in a furnace so that the emissions from the furnace meets the requirement of the environment, meets the environment stringent environmental norms of stack emission. So that's all. So in today's session, what we have covered mainly primary processes like CDU, VDU, secondary processes like CRU, CCRU, secondary processes, contaminant removal processes like DSDS, DSDT, video upgradation processes like FCC, hydrocracker, and vacuum residue upgradation process like delayed coker unit. So that's all. I think.
Okay, thank you, Mr. Sen, for a nicely explanation of what is happening in the refinery. Participants, if you have any question, please let us know. Students, you should have some questions at least, because Mr. Santanu Sen is from industry, so definitely he will resolve the issues in case anything comes in your mind, how to handle that.
It is really excellent, Mr. Shen. Asunenduda, hello.
I'm just checking with the questions first. Yeah.
Yes, yes. It is really excellent.
Yeah.
I have no words to express my thanks. So please carry on with the formal
Yeah,
things.
that's true, sir. Okay, I have a question, Mr. Santonu.
Yes, sir.
You can say it's a curiosity also to know. It's not a question as such. You had explained in your 1 hour talk that how the commercial scenario have been given importance for any refinery, so that not only the technical aspects of the products to be sold, but the profitability can be maximized. Okay.
Yes, sir.
I think both the things you had covered, the quality of the products, how to get it improved so that it can be marketed without having any problem. At the same time, how the proportion of those finished products can be done in such a way that because of the difference of pricing for the products, the maximum profits can be done by any refinery. Am I correct?
Yes,
I
sir.
think, yeah. So in case it is like that, now the question comes or the curiosity comes that the price of, for example, whatever product you are talking about, it seems maybe 35 to 40% of your product goes in terms of petrol, and maybe 30 to 35% goes in terms of diesel, and remaining are as LPG or naphtha or other products. If that is so, the differential price between petrol and diesel is not similar what we have seen for the last 15 years, because earlier that difference was quite more, the price between petrol and diesel, and now the difference is in that way quite less. So do you think that some of your units will be underutilized, which might have been introduced because of that much of price difference?
Yes, definitely. We have the flexibility. Say, in case MS and HSD price differential is favorable, then we have to go for maximization of MS to some extent by reduction of diesel. So in that case, whatever processing capabilities are there in diesel processing units, those may get underutilized, and the MS processing units or the catalytic reforming units, those maybe it will be required to run those units at the highest capacity. Or we can source reformate from other units like Paradip, which is supplying reformate to Haldia refinery, because Haldia is going to maximize MS. The similar thing happens in naphtha and MS also, because naphtha, it is going to the petrochemical processes. Sometimes the margin in petrochemical processes is too high, so substantially the naphtha prices will go up. Situations may arise to this extent also. Naphtha prices are higher than MS also. In that case, we have to minimize MS and maximize naphtha, and send those naphtha to our petrochemical oriented refineries like Panipat and Paran, specifically Panipat, which is having naphtha cracker. So if MS and naphtha price differential does not permit MS to be maximized, we maximize naphtha and feed to naphtha cracker, which is at Panipat refinery. Similarly,
okay, that I understood. Basically, to take care of that, the different refineries are having configured to address to that situation. But in any particular refinery, suppose Haldia, for example, once
yes,
it has already been built up with certain concepts.
Yes, Indian oil refineries are not running in standalone basis. Always there is a stream sharing between all the refineries.
Okay.
So we can, this is our strength.
Okay.
We can send some material to other refineries where the requirement is more, or we can take material from other refineries which we are wanting, which we are wanting. Because say reformat, if reformat is not there, we will ask Paradip to send us. If naphtha is excess in our refinery, we will ask Panipat to take naphtha. So none of the Indian oil refineries operate on standalone basis. It is an integrated company having 11 refineries all over India.
Okay.
Sometimes it happens like that also in naphtha during the pandemic situation when naphtha prices were encouraging because of the higher petrochemical margin and lower MS demand during the pandemic scenario last year or this year also. We normally process naphtha into our GTs, gas turbines. We segregated naphtha from GT field and operated the GT in ATF mode because those in those days ATF was not getting sold because of the pandemic scenario. Payments are restricted, so we reduced ATF. We sent part of the ATF to DSDS or DSDT for diesel production. Diesel was also having problem in evacuation. That time, we preserved some amount of naphtha by feeding GT with ATF, and that naphtha was sent to Panipat for cracking because petrochemical margin was promising.
Okay. I mean, a lot of combinations are possible at the same
Yes,
time.
lot of configurations are possible,
and at the same
Haldia
time,
refinery, which is having complexity index to the tune of 10.35, has multiple flexibilities to align it to the market situation.
Okay. Thank you. I think it's a very nice explanation, both commercially as well as technically also.
Yes,
is there any other question? Okay, then I'll call the next speaker. But before that, Swamiji, if you have to say something for Santanu, please.
No, I really enjoyed the presentation. Generally, sometimes it happens like that, I mean, listening all the presentations, that is not possible for me, but this time I have seen the total presentation and I could brush up the student days knowledge regarding this, along with some upgradation, particularly last few minutes, what he was telling about the, future refinery endeavors, etc. So that is really good to know. So I am very grateful from the standpoint of our organization and standpoint of Jadavpur University, on behalf of our chairman and course director. So let me express my kind regards and gratitude to Mr. Shen. We hope that we will be having a strong, association with IOCL in future also. With this hope, so let us have a formal clapping to him, Mr. Shen. Okay. Thank you very much. He is a product of our Ramakrishna mission, so that is why that also I got very much elated to know all these things. Thank you, sir. Thank you, please.
Thank you.
Aswanindu, you please introduce my friend Dr. S.K. Das, the former head of the Department of Chemical Engineering, University of Calcutta, and also the professor and council member of Indian Institute of Chemical Engineers. So please introduce Dr. Das.
Okay. Mr. Sen, I'm sorry I called your first name only sometimes. Mr. As Santanu only, okay?
Nobody minds, because it is you can say in Bengali the antarikata. So
actually it came from that only. That's why. But I should not say so. I think it seems. Sorry, Mr. Santanu Sen. Okay. Now, students or participants. So, as you have already seen the picture of Mr. Sudeep Das, so I would like to invite him for our next lecture. As you have already seen this particular lecture of petroleum reforming, although it has been explained very nicely in a technical as well as commercial way by the person from IOC, who is from industry. I think the same thing we need to again listen in a different fashion, because this is undoubtedly a very important aspect, the reforming operations in refineries. Because all the petroleum products which we are using, ultimately it's coming from crude oil, and that processing is required to be known many times even. A single time listening may not be sufficient. So from that perspective, we will have the same or the similar topic will be from Dr. Sudeep Kumar Das. He is currently the professor and former head in the Department of Chemical Engineering, University of Calcutta. He has completed his PhD and MTech in Chemical Engineering from the Indian Institute of Technology, Kharagpur, and graduated from the University of Calcutta in Chemical Engineering and Chemistry honors. He is also actively engaged in research related to different fields of chemical engineering. There are many, I mean, fluidization, multi-phase flow, adsorption, and removal of pollutant from wastewater, safety, fluid dynamics, artificial neural networks, and glass ceramics. He has published one book, 15 chapters, more than 200 papers in national and international journals, and presented a large number of invited lectures in the conferences. He has been reviewer for more than 125 national and international journals. He was recipient of Indian National Science Academy Visiting Research Fellowship Award in 1999-2000, Research Ratna Award in 2019 for Best Researcher in Environmental Engineering, the Bharat Jyoti Puraskar in 2018, Indira Gandhi Gold Medal Award in 2016, Best Citizen Award in 2015, Dr. Radhakrishnan Gold Medal Award in 2015 and 2014, and Outstanding Faculty Award in 2015, Best Citizen of India Award 2015, Bharat Gaurav Award 2014. In fact, some more awards are there. We will, of course, we can find out all these details from each Google website also. He is at present serving as honorary secretary, honorary treasurer from Indian Chemical Society. He also served as honorary secretary and honorary treasurer in Indian Institute of Chemical Engineers many times. He also acted as chairman, Calcutta Regional Center, Indian Institute of Chemical Engineers, honorary secretary and honorary treasurer for several years in the Calcutta Regional Center, Indian Institute of Chemical Engineers. So I think we should not take more time for detailing all those things. It's better if we try to get more and more valuable information from him. So Mr. Dr. Sudeep Das, please, stage yours.
Thank you, Asanandu. I'm extremely thankful to the Swamiji to invite me to deliver a lecture on reforming operation used in the refinery. Petroleum refinery produces LPG, motor gasoline, jet fuel, kerosene, diesel oil, distillate, fuel oil, residual fuel oil, lubricant, asphalt, bitumen, etc., and other products to the distillation of crude oil or through the redistillation, cracking, reforming of crude oil, or through redistillation of these products. There are mainly three types of refineries like this. One is topping refineries, hydrospinning refineries, and upgrading refinery or complex refinery. In India, almost all refineries are upgrading type or complex refineries. In topping refineries, have a crude distillation column and a product naphtha and other intermediate products, but not gasoline. There is a few tapping refineries exist in the USA, particularly in the area of Alaska. In hydroskimming refinery, have a mild conversion unit, such as hydrotreating and or reforming unit to produce finished gasoline products and they do not upgrade. They do not upgrade heavier components of the crude oil that exist near the bottom of the crude distillation column. Some topping and hydroskimming refinery specialized in producing heavy crude oil to produce asphalt. There are 8 operating asphalt plants and approximately 20 other hydroskimming refinery in USA as on 2006. So the vast majority of the refinery in USA and all over the world, more than 80% or 85% of the refineries are on upgrading or complex refinery type or conversion refinery type. Yeah, these refineries are cracking, coking operation converts long chain high molecular weight hydrocarbons, that is heavy distillates, into smaller hydrocarbons that can be used to produce gasoline product or lighter distillate and other higher value products and the petrochemical refinery feedstocks. Main purpose. This figure shows a typical refinery scheme. Flow of intermediates between the process will vary by refineries and depend on the structure of the refinery, type of crude processes, as well as the product mix. First, process unit, and nearly all the refineries is a crude distillation unit, that is atmospheric distillation unit, and different conversion processes are available using thermal or catalytical process, that is delayed coking or other different types of coking, catalytic cracking, catalytical reforming to produce a desired mixed product from the crude oil. The products may be treated to upgrade the product quality, that is sulfur removal, like sulfur removal using hydrotreating or hydrodesulfurization unit. Tight processes that are used to condition inputs or produce hydrogen, or the product include conditioning, that is desalting, hydrogen production, power and steam generation, and the asphalt production. In general, lubricants and other specialized products may be produced at special location in a specialized manner. Now, if you think of global liquid, consumption of global fuel, crude oil spot price average $75 per barrel in July this year, up to $5 per barrel from June increases, and up to $25 per barrel from the end of 2020. This price has been rising in nature this year as a result of steady drawn of global oil inventories, which average 1.8 million barrels per day during the first half of 2021 and remained as much as 1.4 million barrels per day of July. We expect the price will remain nearly same the remaining of this year, and expected that is slightly growth or slightly decline in the next year, around of $65 to $66 per barrel. It was estimated that around 98.8 million barrels per day of petroleum and liquid fuels were consumed globally in July, an increase of 6 million barrels per day with respect to 2020, but 3.4 million less than the July 2019, and this is due to the pandemic situation of COVID pandemic situation. In India, oil demand and expect to grow by 480,000 barrels per day in 2021 after a sharp contraction last year, which generally account to close up of growth of the economic condition of India. Apart from being channeled into the manufacturing, agriculture, and industrial sector, analysts have also said that up to 85% of Indian oil demand from the are coming from are for the road sector, with countries' massive transportation network with of interstate buses, flights, trains, etc. So demands of the liquid fuel for the gas for the road sector, that petroleum, motor vehicle, truck, etc. That is the gasoline and diesel is increases. According to the PPAC, that is Petroleum Planning and Analytical Cell, are forecasted that financial year 2021 to 22, the oil, particularly transportation purpose, used in transportation purpose, consumption was 83.77 million metric tons, a 16.36% increase from the 2020 and 13.30 increase from its previous forecast of 2020, 2021, 2021. The role of liquidity and overall dollar weakness, also the important parameter for the cost analysis of the oil prices. We have large number of refineries, and one of the biggest refinery is Jamnagar by Reliance Petrochemicals. They built 33 million metric ton per annum in 1999 and 35.2 million metric ton per annum in 2008. Overall, Indian refinery capacity is around 249.9 million metric ton per annum, and crude oil is processed 54.4 million metric ton per annum in 1990-20 and 221.8 million metric ton in 2021. Due to pandemic situation, the production rate is slightly lower, and India also export large amount of petrol and diesel to the other countries. The MS production in 1920 is 38.6 million metric ton, and consumption is around 30 million metric ton. And 2021, 35.8 million metric tons, and consumption is 28 million metric ton. If you think the cost-wise, the crude price cost in average crude price cost in 1919-20 is $60.74 per barrel, whereas 2021 $44.82 per barrel, and May 2021 is $66.95 per barrel. In petrol, in 1990 to 1920, 66.94, 2021 47.68 and 74.42. Similarly, diesel also slightly less than the crude oil price, petroleum oil price. So we are discussing the importance of the gasoline, particularly in this sector. Demand today, automobile requires high octane, and this can be one of the route is obtained from the reforming operation. And this required low sulfur content, low benzene content, limited aromatic content, limited olefin content, and should not contain any lead component into the system. Catalytic reforming unit generally produce around 30 to 40% of the gasoline demand all over the world. But depending on the requirement for implementing the stringent regulation, particularly in Bharat 6, number of pre-treatment is also necessary for this operation. So this is the European gasoline specification 2020, 2000, 2005, 15, and ultimate severity is not yet implemented. And in Indian specification gasoline, Bharat 3, Bharat 4, and Bharat 6, sulfur should be less than 10 ppm in 10 ppm Bharat 6, and IOC and all the refineries that are trying that the sulfur content in the gasoline less than 9 ppm. Aromatic volume maximum is 35, olefin 21, benzene 1, oxygen 2.7%, vapor pressure 60 and kPa. And RON, MON 98, 91, 81 in Bharat 6. So new gasoline specification requires a high octane level, meeting the reduced sulfur specification, meeting the reduced aromatic and benzene specification. Constant from the highs or constant from straight run gasoline, that is initial fraction of the crude oil to give gasoline cut with a low octane number. 3/4 of the light gasoline, that is contains C6, C5 to C8, C6 component. RON varies between 60 to 70. And 3/4 of the heavy gasoline, which is C7 to C10 component. RON varies from 30 to 50. So very low RON number. So RON or MON, such octane number can increase by chemical transformation. So light gasoline can be isomerized. That is normal paraffin can be isomerized to isoparaffins. That is normal hexane. RON is 24.8. 2,2-dimethyl butane. RON is 91.8. So increase of octane number takes place. Heavy gasoline, catalytic reforming process, normal paraffin, naphthalene, they can be converted to the aromatic. That is cyclohexane, RON is 83, whereas benzene is RON 108. That can be possible. On that background, we will clear our catalytic reforming process, the fundamental of the process. Objective, reaction, some are desirable, some are undesirable. Process, semi-regenerative, fuel forming, continuous catalyst, regenerative. Next, the process variables, reforming catalyst, ties, poison, and some recent advances in the reforming operation used in the refinery process. So what is the purpose of the refinery? Purpose of the reforming unit in the refinery is to produce high octane reformate, which is the main component of motor fuel, aviation gasoline, blending or aromatic rich feedstock. We will get hydrogen rich gases. Due to nature of the reaction, reforming process also produce LPG, fuel gases, etc. Purpose of the reforming is either reforming feed is either low quality straight run naphtha or cracked naphtha, generally mixed with straight run naphtha. Reforming feed must be pre-treatment. Pre-treatment is necessary due to presence of contaminants in all cases and the specific characteristics of the cracking naphtha. Cracked naphtha. Naphtha pre-treatment unit is or are always necessary for the feedstock. Typical feedstock and product. Una analysis is paraffin, olefin, naphtha analysis. Feed content 45 to 50 paraffins and product content 40 to 30 to 50 product, 50 paraffins. This is weight percent. Olefin is 0 to 2, product will 0. Naphtha 30 to 40, product in 10 to 5 to 10, aromatic 5 to 10, and product is 45 to 60. This is this paraffin and naphtha. This aromatic is important ingredients in the reformat product, which is responsible to increase the number, and also the paraffins, which is normal paraffin, which is converted to isoparaffin, is responsible for the increase of the octane number of the product. Types of gasoline is used. One is LSR gasoline, that is C5 to 82 degrees centigrade gasoline, is largely composed of lower molecular weight paraffin. And another is boiling range above 0.04 degrees centigrade. So feed must be composed of C5 gasoline, LSR gasoline to 0 degrees centigrade up to 20 degrees centigrade fraction of the gasoline. Lower molecular weight, if we feed in lower molecular weight in the reforming unit, it will produce butane and lower molecular weight component, the gaseous component. So it is not economical in the process. And hydrocarbons above the boiling range 204 degrees centigrade are easily hydrocracked at the operating condition and cause excessive carbon deposition on the reactor, on the catalytic plate. Two types of reaction generally involves increase the octane number of the product. One is desirable reaction, which lead to a higher octane number and to high purity hydrogen production. They are reaction to promote. You have to promote this type of reactions. And there is adverse reactions, which lead to decrease in octane number, decrease in hydrogen, and they must be minimized during the reaction. So optimization parameter is also important. So we will try to maximize the desirable reaction and minimize the undesirable one. This chart is given cyclohexane, RON, methyl cyclohexane, RON, all this type ROS and given. So if you cyclohexane, if we convert to toluene, then 83 we can increase 120. Methyl cyclohexane to methyl xylene or toluene 120. So that is the aim of the reforming unit. Desirable reactions with hydrogen production. So here, series of complex chemical reactions occurs. Some are desirable and some are undesirable. Reaction conditions have to be chosen that favor the desirable reaction and inhibit the undesirable reaction. Desirable reaction in the catalytic reforming unit lead the formation of aromatics and isoparaffins. That is, paraffins are isomerized. And to some extent converted to naphthens. And then naphthens should be converted to the aromatics. Olefins are saturated in presence of hydrogen, because once the naphthen is converted to aromatics, hydrogen is generated. So all types of aromatic compound which is present in the feed must be saturated at that condition. Naphthens are converted to aromatics. Aromatics left, which is in the feed, are generally not reacted and left as such in this condition. And there is also some undesirable reaction like de-alkylation of the side chain on the naphtha and aromatic form butane and lower hydrocarbon products, lower gaseous products, cracking of paraffins and naphthenes to form butane and lighter products also. So first desirable reaction is naphthalene dehydrogenation reaction. This is the basic reaction. This is a basic reaction. So naphthalene compound are dehydrogenated into the aromatics, which produce 3 moles of hydrogen per moles of naphthenes. This reaction is promoted by the metallic function. This reaction is highly endothermic in nature. So thermodynamically, it favors at high temperature and low pressure, and high number of carbons. Kinetically, it favors at high temperature, high number of carbon, not affected by hydrogen partial pressure. At the selected operating condition, the reaction is very fast and almost totally complete during the reaction period. Now, paraffin hydrocyclization. Paraffin hydrocyclization. These are multiple step reaction promoted by both acid and metallic function of the catalyst. Kinetically favors by high temperature and low pressure. Dehydrogenation step become easier as paraffin molecules weight increases, but is completed by hydrocracking reaction. When the molecular reaction is very high. So at a selected operating conditions, much lower rate, then its rate is much lower kinetic rate, and that of the dehydrogenation reaction. Linear paraffin isomerization, promoted by the acidic function of the catalyst. Hence, it is slightly exothermic reaction. Reaction is fast. Thermodynamically depends on temperature, pressure. Kinetically favors at high temperature. Not affected by the hydrogen partial pressure. Not affected by the hydrogen partial pressure. C4 is converted to percentage of isoparaffin is 45, 44 at 500 degrees centigrade. C5 to 55% isoparaffin. C6 is converted to 70% isoparaffin. 75% C7 is 80% isoparaffin. And C8 is 88% isoparaffin from straight chain to isoparaffin. Transformation is possible at 500 degrees centigrade. So naphthene isomerization. Another very important reaction is naphthene isomerization. Desirable reaction because subsequently dehydrogenation of the alkyl cyclohexane to the aromatic component. Difficult of the ring regeneration or the difficulty of ring rearrangement and high risk of reoffending, that is paraffin is also possible. At a selected operating condition, theoretically at low rate, but subsequently dehydrogenation of a shift reaction followed a desirable reaction. Desired reaction. This reaction is slightly endothermic. It's endothermic in nature. Easier reaction, which gives high octane number of the final product. Undesirable reactions is hydrocracking reaction. Hydrocracking affects either paraffin or olefin compounds, promotes both acidic and metallic function of the catalyst, favored by high temperature and high pressure. And this is a highly exothermic reaction. So there is a possibility of runaway reaction if we do not maintain the proper reaction condition or maintain the proper condition, or we cannot extract the heat of reaction. At a selected operating condition, hydrocracking reaction will be complete, but is limited by kinetics. That is the advantage of the process, is limited by the kinetics. What is the consequence of the cracking? Decrease the paraffin, increase of aromatic proportion, increase of octane number, decrease in hydrogen production, because cracking reaction consume hydrogen. When the molecule is cracked, one double bond compound is produced. The double bond compound at a operating condition at presence of hydrogen, so should take the hydrogen to become a saturated. So decrease the hydrogen production, increase the yield of light endpoint, that is low molecular paraffin, that is mainly gaseous paraffins are produced, that is LPG range of gasolines are produced, LPG range of products are produced, so increase of light end production is more. Another reaction is hydrogenolysis, which is promoted by the metal function of the catalyst, favored at high temperature and low pressure. This is exothermic, so this of runaway reaction is possible. It also produced methane or ethane type of molecules, that is breaking of the chain. Hydrodealkylation, another adverse reaction, breaking of the branch by the aromatic ring, which is present in the aromatic ring, is promoted by the metallic function of the catalyst, favored high temperature, high pressure, consume hydrogen, also produce methane or ethane, depending upon the length of the side chain, or butane or propane butane. But selected operating condition with selected catalyst, the reaction is not very significant in nature. But proper selection of the operating condition and the proper selection of catalyst is necessary. Another is alkylation reaction. That's the addition of olefinic molecules on the aromatic ring, which is promoted by the metallic function of the catalyst, lead to the heavier molecular weight, which may increase the end point of the product. And also, there is a tendency to promote coke, which is deposited on the catalyst. The activity of the catalyst will decrease subsequently. So this type of reaction must be avoided. Transalkylation, that is alkyl disproportionation. This mutation of two alkene groups, two toluene ring produce a benzene and xylene. And this type of reaction is also promoted by the metallic function. But is favored, only advantage is favored very severe condition, temperature and pressure. So selecting a proper operating condition, selection of catalyst, again this reaction is very negligible in ideal condition. And the next is coke formation. This is also very adverse reaction, results from a complex group of reaction. Detailed mechanism of the coke formation is not fully known. Think heavy unsaturated product is polynuclear aromatics and heavy olefin, traces of diolefin present in the feed or produced during the reaction. Coke deposited reduce the active contact area and reduce the catalytic activity drastically. It favors low temperature and low pressure. In octanizing operation condition, necessity of the continuous regeneration maintains low level of coke on the catalytic surface. If you think the conversion, naphthalene to aromatic conversion is more or less 98%. Methyl cyclopentane produced benzene. Cyclohexane produced benzene. Dimethyl cyclopentane produced toluene. Dimethyl cyclohexane produced xylene. Cyclopentane produced toluene. Methyl cyclopentane produced xylene. If you do the paraffin to aromatic conversion, 1 mole of P6 paraffin, that is 6 carbonate of paraffin, yielded 0.5 mole of aromatic 6-membered aromatic ring, that is benzene. 1 mole of P7 yields 0.1 mole of A7. 1 mole of P8 yields 0.25 mole of P8. 1 mole of P9 yields 0.45 mole of P9. 1 mole of P10 yields 0.45 moles of A11, aromatic 11. Sorry, this should be A. Sorry. It is 1 mole of P8 yields 0.25 mole of A8, and also the 1 mole of P9 yielded 0.45 mole of A9, aromatic 9. The paraffin to aromatic conversion. This should be, sorry, this should be PA8 and A9. All these reactions in series and parallel to each other, producing a complicated reaction scheme. In an effort to simplify the scheme according to the reaction rate, the main reaction takes place in the following order. The first reaction, mainly dehydrogenation and isomerization. In second or third reactor, dehydrogenation, isomerization, cracking, and dehydrocyclization takes place. And fourth reactor, cracking and dehydrocyclization reaction generally takes place. The simple scheme, but the first reactor is responsible for dehydrogenation and isomerization reaction. Second and third reactor for dehydrogenation, isomerization, cracking, and dehydrocyclization. And fourth reactor is responsible for cracking and dehydrocyclization reaction. So naphtha catalyst forming reaction includes dehydrogenation, dehydrocyclization, isomerization, hydrocracking main reaction, which are performed both for metallic and acidic part of the catalyst. Dehydrogenation reaction, metallic function of the catalyst is important. Recyclization, metallic plus acidic group is acidic site is important. Isomerization, metallic as well as acidic functions are important. Hydrogenolysis, metallic function is important. And hydrocracking, metallic plus acidic function is important. Basically, this is highly endothermic transformation. Rate of reaction also varies very widely. So overall amount of catalyst needed for transformation is distributed not equally among the several adiabatic reactors in series with intermediary heaters provided the required heat energy. Naphtha catalytic reforming unit typically made up with an intermediate preheated system. This is a long vertical heat exchanger with large surface area to allow the preheat of the feed to further heating in the charge heater, usually 3 to 4 liters, and reactor in series, and a low pressure separator sub-exists. Hydrogen is flushed and separated in a separator where a part of it is recycled to the need of the feed, again continuous before it entering the first heater, while the heavy liquid is sent to stabilize the pump. So heater generally used in the large surface area, long vertical heat exchanger with large surface area. The feed reheating prior to the charge to the reactor. This is typically a temperature composition inside the reactor. Reactor 1, reactor 2, reactor 3. Temperature gradually decreases. First reactor very sharp decreases, second reactor slightly, third reactor is very slight decrease in temperature. Whereas if the feed content P60, aromatic 10, and naphthalene is 30, then aromatic is increases, paraffin is decreases, and naphthalene is also decreases in the case of third reactor. First reactor, aromatic is increases, and then third reactor is aromatic is increases. Paraffin is more or less same in first reactor. Second reactor is slightly decreases, and third reactor drastically reduces. Whereas naphthalene is first reactor is decreases due to aromatization, dehydrogenation, and then slightly decreases and more or less constant in that reactor. This is a typical feed and product distribution containing 3 reactors. HLR gas handling speed is 180 degree to 380 degree Fahrenheit is the feed. Humidity to reach 99 RON. Pressure is 1124 kPa. Feed is paraffin 16 and nitrogen naphthalene 29 and aromatic 10. First reactor keep PUH 59 N8 and aromatic increases to 33. Second reactor paraffin reduced to 50 and naphthalene is reduced to 6 and aromatic increases to 45. And in last reactor, paraffin is reduced to 29, naphthalene is 5 and aromatic increases to 87%. So this is another typical examples. The industrial reactor catalyst distribution. Reactor 1 is 10%, reactor 2 is 15%, reactor 3 is 24%, and reactor 4 is 50%. Peak of reaction, naphthalene to dehydrogenation is minus 50 kilocalorie per mole. That is an endothermic reaction. Paraffin dehydrocyclization is also endothermic reaction. Isomerization, paraffin and naphthalene are positive. Kilocalorie per mole is positive. That is exothermic reaction, and cracking is also exothermic reaction. The most frequent type of unit used in the industry and current license action UPO and older days is Chevron, Amoco, Exxon, etc. So first is heater and then reactor, interheater, reactor 2, interheater, reactor 3, and then separator, and then distillation unit to separate the product. And this is the low pressure separator when hydrogen is separated and also the hydrogen is recycled along with the feed. Sorry. This is a conventional unit. This is a conventional unit. Reactor preheater, reactor 1, preheater, reactor 2, preheater, reactor 3, and then separator, this compressor, recycle compressor, and the hydrogen rich gas, and the unstabilized deformant goes for distillation to separate different products. A dual forming, this is a dual forming reactor. This part is more or less same, and next part is continuously from third reactor is continuously catalyst is coming, and it will continuously regenerate the catalyst and send back to the reactor. Other part is more or less same. This is also a continuous catalytic regenerative reforming unit. It is also a continuous catalytic reforming unit. Different licenses, different types of system can be used. See, this is volume is lower, then slightly increases, and maximum is this 10, 20, and in that order, catalyst is distributed. The objective of the regeneration system is remove the catalyst so that catalyst can be regenerated. Metal redistribution of the chloride adjustment should be required. Catalyst drying also required. So coke removal is burning zone, that coke is converted to the carbon dioxide. Metal redistribution chlorine zone, the oxychlorination zone should be there, and catalyst drying as calcination zone should be there. Each zones are independent, and each zone should be optimized according to the process condition and input catalyst condition. That is gas combustion from the dry loop, that is primary burner, and then finished burner, then oxochlorinated, chlorinating agent, and water should be added. And it should be whatever effluent is coming, different treatment should be required. And then oxochlorination and calcination simultaneously can be takes place, and then give the regenerator catalyst. Burning with dry gas, primary burner, burning with dry gas. That is, excess oxygen is required, and you have to control the absolute temperature so that this is exothermic reaction, so that catalyst will not destroyed by high temperature. In oxychlorination unit also, of oxygen, temperature and moisture should be properly controlled. And the optimum platinum dispersion should be required so that in calcining condition that should not be hampered. One has to look after this process also. This is the catalyst regenerator, primary burning, finished burning, oxychlorination unit, including agent added, and calcination unit, and then we will get the regenerated catalyst from the unit. Now, what are the process variables? The process variables. Process variables are pressure, temperature, space velocity, hydrogen partial pressure, quality of feed, and operating parameter. What is the summary of the operating parameter? Process variables is pressure, temperature, space velocity, hydrogen partial pressure, that is hydrogen partial pressure, hydrogen to carbon, hydrocarbon ratio, quality of the feed, and operating parameter are tabular form. Each of them can be fixed by the operator, the unit, within the operating range of the equipment and independently from each other. One set of independent variables for the same feed characteristics. There are only one performance of the unit, that is one set of values. For product yield, for product quality, that is octane. For product for catalyst stability, that is coke make, how much coke is made, and product stability. And then first is pressure. Pressure is a basic variable because it inherent affect the rate of reaction. Low pressure enhance the hydrogen production because if you think of the one paraffinic molecules gives one aromatic molecule, one naphthalene molecules gives one aromatic molecule plus 3 hydrogen. So low pressure enhance the hydrogen production reaction, that is dehydrogenation, dehydrocyclization, and also coking reaction. And cracking rate also reduced on the pressure reduced. So the lower pressure, higher yield of reformat is possible, and hydrogen for a given octane number. High coking rate, but also possibility of a high coking rate compensate by continuous regeneration of the unit is possible. Average catalyst pressure used goes to last reactor inlet pressure. It is a highly generalized statement. During transient condition, that is start-up, start-down, or upset condition, it is recommended to increase the pressure to lower the coke formation. So transient condition in the start-up period, shutdown period, or plant is upsetting condition, it is always recommended that increase the pressure to keep the lower coke formation so that the catalyst can be intact. But limits of the operator action, the pressure rise is limited by equipment design pressure. Lower pressure limited by recycle compressor, design power, and intake volume. That part is important. Next is temperature. Most important, the most used operating parameter with the space velocity. Catalyst activity is directly related to the reactor temperature. raising or lowering the reactor inlet temperature, operator can raise or lower the product quality and yield. Commonly accepted consider the weight average inlet temperature can be calculated by this formula. An increase of temperature, major effect, major increase of temperature, the major effect is increase the octane number, decrease the yield of C5 plus fractions, decrease the hydrogen purity, increase the coke deposition. Slight increase of temperature from the calculated temperature to the life of the catalyst makeup or this activity loss. This is possible. Larger and temporary change in temperature are required to change octane at constant feed quality and quantity, to change feed quantity and still remain octane number constant in the product, change of feed quality and still maintain the octane number. The space velocity. Space velocity is can be calculated for weight hourly space velocity, that is weight of the feed per hour at weight of the catalyst in the reactor, or liquid hourly space velocity, that is the volume of feed at 15 degrees centigrade per hour by volume of catalyst in the reactor. It is linked with the residence time of the feed in the reactor and affect the kinetics of the reformate reaction. If phase velocity decreases, residence time should be increases. Higher selectivity, lower octane number increased, lower reformate yield, higher coke deposition, because higher coke will deposit on the catalyst surface. The operator must bear in mind that each time liquid feed rate is changed, a temperature correction must be applied if the octane is to be maintained. And the basic recommendation is always decrease reactor inlet temperature first and then decrease the feed flow rate afterwards. Always increase the feed flow rate first and increase the reactor temperature afterwards. These two conditions always remembered by the operator. Now, hydrogen to hydrocarbon feed ratio. Pure hydrogen moles per hour recycled by naphtha flow rate moles per hour. The recycled gas MW obtained by chromatographic analysis as well as hydrogen volume fraction in the recycled gas. The feed MW is obtained by chromatographic analysis or by correlating from the distillated range of specific gravity, specific gravity. This is a method of operating condition. How to measure this? Operator can change hydrogen to hydrocarbon ratio, lowering or increasing the recycle compression flow. For a given unit, the amount of recycle is limited by the recycle compressor characteristic, that is power, suction flow, etc. Hydrogen to hydrocarbon ratio has no obvious impact on the product yield or quality, but high hydrogen to hydrocarbon ratio reduce the coke buildup. It is strictly recommended to operate with a hydrogen to hydrocarbon ratio equal or higher than the design parameter. Next is feed quality, characteristic of the feed. Feed is characteristic 0.85 N plus A. With a higher 0.585 N paraffins plus aromatics, the same octane can be obtained at lower severity and product yield will be higher. Or in the same severity, octane number will be higher. Higher naphthalene contents, endothermic reaction, heat load is increases, and the feed flow rate will limited by the heater design due. With lower 0.85 plus N plus A content, the higher paraffin content, the hydrogen purity of the recycled gas decreases, and the operation will be limited by recycle compressor capacity. And if impurity is there, temporary or permanent reduction of catalyst activity by poisons containing in the feed. So the feed characteristics is really limited. In reforming process, the molecule, the boiling range of the feed and product are almost identical in nature. We are not changing the boiling range of the feed and product. Our objective is to transform, isomerize, or aromatize, increase the number of the product. That is the main purpose. For that, some desirable, some undesirable reaction is there. Undesirable lead to lower molecular weight component or for formation of the coke, which is laid on the surface of the catalyst to deactivate the catalyst. If we lower molecular weight, that is C5 or 80 degrees centigrade feed, lower than molecular weight, we will get hydrocracking reaction at the reaction temperature. So lower molecular weight component production is more. If we go for the higher molecular weight component, higher boiling range, that is more than 204 degrees centigrade of the feed, then we will get more and more coke formation in the reactor. So that part is very limited. Feed is gasoline range, product is also in the gasoline range. Only difference feed and product is the product feed has lower octane number, product is higher octane number. So the feed distillation range is follow 70 to 100 degrees centigrade, endpoint 150 to 180 degrees centigrade. Lyse fraction cyclization of C8 is more difficult than C8, C7 to C8. So lighter the feed, higher the required severity for a given octane number. So lighter is feed not possible, and also for lighter feed, cracking is also possible at a particular reaction temperature. Heavier fraction, naphthalene and aromatic content, lower severity to obtain good yield, but again the polycyclic compound formation is there, which favors the coke deposition. So endpoint higher than 180 degree is not generally recommended for the operations. So 70 initial boiling point is 70 and final boiling point 180 is recommended feature. Or is slightly above up to 204 degrees centigrade can be accommodated. These are the operating parameters in summary. If we increase the pressure, octane number decreases, such octane number will decrease, reformity will decrease, coke deposition will decrease. Increase of temperature, octane number will increase, reformity will decrease, coke deposition will increase. Phase velocity, increase of phase velocity, octane number decreases, reformity will increases, coke deposition will decrease. Hydrogen to hydrocarbon ratio, if we increase, RON will not affected, reformity will not affected, but coke deposition will decrease. Again, naphtha quality, the feed quality, A plus 0.85 N increases, that RON increases, reformity increases, coke deposition will decreases, end boiling point increases, RON increases, reformity increases, coke deposition also increases, and initial boiling point if increase, then RON increases, reformity increases, but coke deposition will decreases. This is a nutshell of the operating variable in the reforming unit. Now the catalyst. The main characteristic of a catalyst, other than the physical and mechanical property, are its activity, its selectivity, its stability. Activity is catalyst ability to increase the rate of desired reaction and inhibit the undesirable one. Its activity is generally measured in terms of temperature. Selectivity, catalyst ability to favor the desirable reaction and inhibit the undesirable one. Practically, it is measured by C5 plus reformate and hydrogen yield and the stability. The change of catalyst performance, that the activity, selectivity with time, that is the stability. This stability will be mainly affected by the coke deposits and by traces of metal in the feed, present in the feed, you can deactivate the catalyst, particularly vanadium or nickel, or that affects the catalyst activity. measured by the amount of heat treated per unit weight of the catalyst. C5 plus weight reformat yield is also an indirect measure of the stability of the catalyst. The catalyst is generally used fluorinated gamma aluminum with nanoparticles of platinum. Fluorinated gamma aluminum are too strong in acid sites, and platinum promote the metallic side, which promote the hydrogenolysis of the reaction. Stability of the platinum has been improved by addition of promoters like Re, IR. The hydrogenolysis of platinum has been reduced by addition of promoter. The acidity of the chlorinated gamma aluminum has been turned by addition of promoter also. To improve the catalyst stability, the platinum sintering has to be hindered. Addition of promoters, ruthenium or iridium. In addition, Re and IR is alloyed with platinum. The boiling point of platinum increases. Is the sintering possibility is reduced. This is the source, the platinum and platinum plus Re, and the platinum plus Re stability, platinum accessibility. If only platinum, the accessibility is reduced. According with the time. In first case, presence of Re, this is reduced much lower rate than the only platinum. So reforming catalyst or bimetallic catalyst consists of platinum plus promoter on alumina substrate. Lithium and tin are being essential, one of the promoter beside the others. The main feature of the catalyst is high purity alumina support, which gives the high mechanical strength. Platinum associated with ruthenium, high stability and selectivity is there. Platinum associated with tin gives high selectivity. This catalyst, another important parameter is this catalyst has degenerability is there. The combination of these qualities giving the following advantages: high reformat yield, high hydrogen yield, high on steam factors, and low catalyst inventory. Now stability. Normal cause of catalyst aging or deactivation, that is metal sintering, depends on temperature, metallic phase, and presence of chlorine. Deposit on coke on metal and acid side, the coke effect can split. Number one, degree of poisoning of deposited coke and relative coke rate. That is more important, relative coke rate. Selectivity. Desired yield is hydrogen, C5 plus reformat, and low benzene. This is desired yield. Benzene yield can be minimized by free fractionation of the heat, which is present in the boiling range of between 70 to 85 degrees centigrade. Benzene is also produced during the reaction by dehydroalkylation of the alkyl benzene types of material or alkyl benzene types of material or alkyl side chain naphthalene type of material. The loss of desired yield by cracking. Hydrocracking involves metals plus acid sites. Hydrogenolysis involves the metal in presence of hydrogen. This is the loss of desired product due to cracking reaction. As earlier also I told, the catalyst affect the reaction rate to two different function or type of sites, one is metallic function or metallic sites, and in the acidic function on acidic sites. Different types of reaction promote of this type. That is, dehydrogenation is promoted by the metallics. Dehydrocyclization is promoted by metallic plus acidic sites. Isomerization is promoted by metallics and acidic sites. Hydrogenolysis is promoted by metallic side, and hydrocracking is promoted by the metallic and acidic sides. Now, temporary poisoning. Which can be temporary poisoning can be removed with proper activity and selectivity of the catalyst. If we do this thing, then we can restore the activities. The common temporary poisonings are sulfur, organic nitrogen, water, oxygenated organics, and halogens. This should be removed before the feed to the reactor. Permanent poisonings are the main permanent poisonings are the arsenic, lead, copper, iron, nickel, chromium, mercury, sodium, and potassium. Now, what type of reactor is used? Generally, two types of reactor is used. One is axial fixed bed type of reactor. That is lower side, the packed bed or other ingredients to support the catalyst bed. And after that, catalyst bed that is lower side, and particularly this side, lower side, and particularly this area. One has to put ceramic material, inert ceramic sphere of 1 inch OD diameter. The diameter ball type of material to support the catalyst bed, and then at the top, a skin should be there to hold up the catalyst. An inner layer must be a refractory lining of the catalyst of the bed. So catalyst, the reactant is coming from the top and going into the input from the top, and output is from the bottom of the reactor. And there is number of places one has to measure the temperature of the reactor by introducing the probes. Permanent probes should be there in the reactor bed. Another is radial fixed bed reactor. Most of the reactors are radial fixed bed reactor, modern design. The upper part of the reactor is made up to account the density change that is settling, possibility of bypass of the catalyst, and space for mechanical assembly. Catalyst jet space also there. Catalyst jet space also there. Previously it was not there. So we discussed what is reforming, what is the potential use of the reforming, what is the reaction, what are the operating variables of the reaction, variables in the process, type of reactor is generally used. Is a batch, semi-batch, or continuous process may be used in the reforming process. Continuous bed as continuous regeneration of the catalysis takes place. And what are the types of reactor used in the reforming units? The reforming unit is used mainly value-added product, a refinery unit. In the profitability of the unit, but main thing is boiling range of feed and product is more or less constant. Boiling range of the feed and product is more or less constant. Only the changes takes place during the reaction. That the isomer is that straight chain compound is converted to the isomer. Naphthalene is converted to aromatic to increase the octane number of the product. When the large number of straight chain compound is there, then it is better not to go for this type of reforming, but straight to go for the ethylene production unit. That is more economical than this, because straight chain compound to convert to aromatic compound is difficult. If the naphthalene compound is more, the 0.85 N plus A is there. So in this type of incident, then one should go for the reforming unit to increase the aromatic compound. Thank you all.
Okay, thanks. Thank you, Dr. S.K. Das, for wonderful presentation. In fact, through your presentation, we could learn the technical aspects, what is to be taken care to maximize the requirement production. Participants, if you have any question, please ask.
Mr. Mondal, it is not only the excellent presentation, it is a way of explanation.
Yeah.
Since the speaker has got such a beautiful command over the subject, the students, they don't know. Sir is the in charge of that master's program in chemical engineering department on petroleum engineering. So naturally, he has got a very wide and thorough, grasp of the subject. So it is so beautifully explained everything. So we are very happy. And here I express my grateful thanks to Dr. Das as well as to Mr. Roshanendu Mondal for the excellent program.
Thank you, sir. Thank you, Samaji.
Yes.
If students have any question, they can directly mail me or telephone me. I am ready to answer.
Yes. And other thing is that we will have one, interaction session. At the almost at the back end of this when our course will be. Ultimately, there will be evaluation in the second week of next month. So there, the students can also put forward the questions, and those are the panelists. They can answer that. Okay. Thank you.
Okay.
Thank you very